In this video, I'm going to be talking about Hooke's law, what all the variables mean, and how to find a spring constant experimentally. And then we're going to go ahead and talk about what elastic potential energy is, and then how to solve for that using this apparatus. So we have a mass attached to a spring, and then once we release it slowly, it's going to stretch the spring out a certain amount. And if you take a look at Hooke's law, the force from a spring equals negative kx. And the force is the force of the spring in newtons. The K is the spring constant, which basically tells you how stretchy the spring is and how many newtons of force are required to stretch it 1 meter. And then lastly, we have the X value, which is the amount of stretch or compression of the spring. Now, the reason why there's a negative here is because that spring force is always a restorative force. And what that means is if something is pulling it down, then the spring is opposing it and then pulling it up. It's basically always going to be having a force that is a restorative force to push or pull it back to its equilibrium position. Now, what you can do is if you hang varying masses from this spring, then you would have a bunch of different forces, and those forces would just be the mass in kilograms times g 9.8. Now, if you know the mass is applying that certain force downwards and the spring is keeping it at rest, then the spring must be pulling up with that same exact force. Now, if we plot the forces along the y-axis, that's going to be useful for us in finding the spring constant. You'll see why shortly. And then if you just measure the amount of stretch from here to here in meters, then we can go ahead and then plot those x values down here. When you plot those, you're going to get a linear relationship that's going to look something like that. Now, if you find the slope is going to be the change in force, the change in the y values, divided by the change in the x values, which are the x distances for the compression or stretch. Now, if you take f divided by x, you actually get k, right? If you divide both of these sides by that x value, then you're going to end up getting k. So it turns out that if you find the slope, that is actually the spring constant. That's the average amount of newtons necessary to stretch the spring 1 meter, and then you can go ahead and find the spring constant that way. So let's go ahead and analyze this system over here and then take a look at the gravitational potential energy, elastic potential energy, and we're going to go ahead and find a K value based on the amount of stretch the spring has. Now, if we're having an object go from here to here, it's changing its amount of gravitational potential energy. So there's definitely a change in its gravitational potential energy, and that change would equal the amount of elastic potential energy the spring would have. The kinetic energy is a non-factor there because this one is at rest and then this one is at rest as well, so there's no change in kinetic energy. So which means that the mg final minus the mg h initial is going to equal the elastic potential energy of the spring, which is 1/2 kx squared. Now, let's go ahead and put some values in with these. So let's say, for example, that our masses are 2 kilograms and that our amount of stretch is 20 centimeters. Now, when we're finding a change in gravitational potential energy, you can always pick your baseline height. So we'll say because this is the lowest point in our problem, we'll give this a baseline height of 0 right over here, which would mean that this height over here is at positive 20 centimeters. So if we were to plug in our values, we would go ahead and say that the mass for the block is 2 kilograms, our G is 9.8, and then our HF, which is our final height here, is actually just going to be 0, which is all going to cancel out. And then we would have negative 2 kilograms times 9.8 times our initial height, which is 20 centimeters. And if we convert that to meters, it's going to be 0.2. Now, if we take 2 times 9.8 times 0.2, we end up getting negative 3.92 joules as our change in gravitational potential energy. Now, if gravitational potential energy loses 3.92 joules of energy, then elastic potential energy would have to gain 3.92 joules of energy in order to keep the total amount of energy consistent. So if we have 3.92 joules of now elastic potential energy, that equals 1 half kx squared. And we know that the x is the amount of stretch, and that amount of stretch is 20 centimeters, which again, we converted to 0.2, and then that's squared within the formula of 1 half kx squared. So if we can go ahead and do 2 more steps, which is multiply both sides by 2, and then we have 7.84 divided by the 0.2 squared, then that would leave us with our k value, and then our k value would equal 196 newtons per meter. So when you're taking a look at a system such as this, where a mass is hanging from a spring, you're definitely going to lose some gravitational potential energy, but that's only because it's transferred to the spring in the form of elastic potential energy. So this negative 3.92 is given to the spring, which then you can set equal to 1 half kx squared, and then go ahead and solve for that spring constant. So I hope that was helpful in helping you take a look at Hooke's law and also how to analyze a hanging spring system to find the spring constant using some energy analysis. Thank you for watching and listening.